Hello and welcome to Fernbank Link's first virtual FLO training. This particular training is geared toward robot design and strategy to help you wow the judges, build your team, and help you program your best machine. Throughout each session, our core values expert will teach you all the core values you need to lead your team to victory. First, what is a strategy? A strategy is a plan that you put together to help achieve your mission and goals. In FLO, everyone on the team should understand the missions and read the challenge guide and always stay up to date throughout the season. It is helpful to create worksheets with all your missions. That way, you can keep track of everything you're going to do throughout the season, including your missions, your attachments, and the sensors that you use. And it's also good to add your code, but we will talk about that in the next series in programming. Explaining your team strategy. As I put in the example here, this green line represents a run. So each time you leave the base is called a run, and you can draw it with a different color. For example, I use the green. So you see I go forward, then I stop at the traffic jam, I do that mission, then I go back and I go toward the swing, I complete that mission, then I go back to the base. So when you do that, that shows the judges how you use your team strategy and how you demonstrate your strategy so that the judges know exactly what you were thinking and what you were coming up with at that time. We recommend that all the team members create the strategy because this is an important part of team building, and everyone should put their idea in so that everyone has a part. That's one of our core values, teamwork. What questions do you ask your team when you're planning? So you want to know which missions are near the base and can be done quickly, which missions can be grouped together because of their proximity and closeness to the base. We want to know which missions might use the same attachment or tool to complete it. We want to know if missions are harder than others or if they're harder to get to from the base. And we want to know what your team goals are for the year when it comes to the robot game. And you want to determine how many points the mission is worth. It always comes down to your points and your core values when it comes to FLL. So I'm going to play a video by Mr. Hino.
Okay, so let's go ahead and start with just color matching. Now, the only colors you're going to be able to match are red and tan. Since there's only this one red circle here and there's that tan circle here. You're already getting points for that white circle, so we're not considering that a color match as far as something that your team can do. So let's go ahead and just take a look at this red unit right here and just talk about the points. So let's go ahead and just separate the red from the stack. So this right here, just because this red matches the red circle, you're going to get 10 points automatically. So it has nothing to do with the height of your stack. It just has to do with the unit matching colors. So because this is red and it's in a red circle, 10. So we're going to take those 10 points and set it off to the side for a second. And now we're going to go ahead and count levels. So because this has 2 levels, right, 1 and 2, you're going to get 5 points per level. So that's going to be 10. So you're going to get 10 points for the 2 levels. So 5 plus 5, and then the 10 points for it matching red. So that's the way you're going to get points for this particular stack here. Now, if this were somehow different like this, so now you're not going to be getting those 10 points for the color matching because it's not completely in the circle. But you still will get those 10 points for this being a stack. So it's basically partially in. Just like that would be partially in if I'm looking at this above the circle. So no matter how this stack is in, as long as it's partially in, and ref is going to hopefully give you the benefit of the doubt, that would be still considered in. And the ref would hopefully have the benefit of the doubt in giving you that. And hopefully that would still be worth 10 points. But you can see the difference. If I push this in completely, it just went from 10 points to now being worth the 20 because this is now completely in the circle. Okay, so now let's talk about a bridge stack compared to just a single stack. So your team probably wants to avoid doing something like this. These stacks are separate. They are not bridged. So if your team did this, let's say it just stopped right there. Your team would get, you wouldn't get the complete 10 points because this is not completely in the circle. But let me just basically talk about the bridged and not bridged. This is not bridged because, they're two different stacks. So I would only get 5, 10, I would only get 10 points for this whole thing because this is not connected to this in any way. So you're not going to get points for this stack right here. So let's go ahead and compare. So this would be 10 points, but let's say your team did that. This would be considered bridged because this is now stacked connecting both of these stacks. So now you would get, notice the difference, you would get the 5, 10. So basically now we can count all the stacks here and you would get 5, 10, 15. So this would be now worth 15 points instead of just the 10 because these are now stacked. Obviously, if you want more points, you would stack this a different method. This would not be the greatest setup just because it's also very wide and it doesn't necessarily fit into there very well. I mean, look how perfect you'd have to be. But anyway, even if you're not, perfectly in, this still would be better than if it was like that. So it's just a matter of bridging what you need to just to make sure that if you're not completely in the circle, you're still getting the most points you can, even something like that. Do you see how this is bridging the two pieces together? So again, it's a difference between if I'm leaving it like that, that's just only worth 10. If I bridged it, now I get the 1, 2, 3 levels, and that's worth 5 more points than if I had left it the way it was. So here's now a case where you might not want to bridge your units together. So right here, if we were to just leave it like this, these are considered two different stacks. So that would be 5 and that would be 5. This would be worth 10. If I did this, it's still worth 10, 5 and 5. Now watch this. If I bridge these like this, I'm still only getting 10. I still only have 2 levels. But if I do this, do you see now that they're two separate stacks? So now this is worth 5, 5 and 5, that's 10, plus this is 15. So now you can notice how in this case here, bridging it is not necessarily the way you want to go in this case here. So it all depends kind of on your design and build setup. You can see here how this separating your stacks will give you more points than if we bridged it. Okay? So the only time that bridging it is going to make it better for you would be like in a situation where the bridge actually connects. See, this would be where you'd want to bridge it. If you did it like this, now you can see how that doesn't help you out because you would only get credit for this unit here. But if we're completely in, it would be better to have it separate like this where you can get a point for each level rather than bridging it where now you only get points for this one level and that level.
As you heard Mr. Hino say, that the different strategies that you use, for example, when he used the 2 blue cubes, if they were bridged and in the square, you would get less points than if they're separated. That's an example of how planning and different strategies can help you acquire more points during your missions. Looks like our core values expert has a message for us.
What about me? sure everyone is working and not just playing around. Once everyone's incorporated, productivity will astound.
When you work together as a team, your productivity and your output will be greater than as if you work together, well, not work together, but then if you work alone. So always work together because teamwork makes the dream work. Okay. Now that we've finished talking about our strategy, we're going to move into robot design. And there are 8 factors of robot design: size, balance, sensor placement, arm and motor placement, wheel choice, attachments, navigation, and cable management. First, we will start with size. When you are planning on the size of your robot, you always want to check the rules and the base height limitations. For example, in 2019, the height of the robot was 12 inches. And so you just want to keep track of that. That all comes into play when you're keeping track of the challenge updates and the guidelines. There may be other height limitations caused by size, either shape or the location, or say you want to go under a bridge in your mission, or there's a certain place you want to go and there's a tight spot. You want to take those missions into account when you're planning on the size of your robot. Next, we'll talk about balance. You don't want the robot to be weighted on either other side. You want it to be equal and even. So because if your robot is unbalanced or unequally leveled, it could cause your performance to veer off. So your robot could go straight and then start turning. And you never want that to happen when you're in the middle of a mission. So you always want your robot to be balanced and leveled. Now we're going to watch a video about sensor placement.
In this video, we will be talking about the placement of sensors on your robot, but we won't be talking about the ultrasonic sensor because we don't recommend using it. So that leaves us with the color sensor, the gyro sensor, and the touch sensor, which will all help your robot navigate across the mat. This is the gyro sensor, which measures how many degrees it rotates. This can be useful when you want your robot to turn a specific number of degrees. These red arrows on top show what direction it's rotating in, so you want it to be facing up or down so it can measure the turn side to side.
Now we will be talking about color sensors or light sensors. If you notice on the map, you'll find these lines running across it, and these are meant to help you maneuver your robot accurately across the map. That's why we have these color sensors to detect them. If you also notice, some lines are branching off of others, and that's where we utilize 2 color sensors. One will be following the main line, and the second will be looking for that second line branching off of the first. That way, we'll have an exact position on the map. If you notice, we have these color sensors about half a centimeter away from the ground with these color sensor shields built around it. These are used to prevent ambient light from affecting our sensors. You should place your color sensors not too far away from your motor and not too close. The reason is the color sensor will be taking information and transferring amount of degrees to your wheel, and if it's too close, it will be reacting too quickly to the information, and if it's too far, it will be reacting too slowly. A good position is having the middle of your wheel in between the end of the motor and the start of the color sensor. I'll be teaching you guys how to make a light sensor shield. So first, you want to make a square with a 2x2 hole in the middle out of these right-angled pieces. Next, you'll want to attach your color sensor to the shield with these angle changing pieces, like so. If you notice, the color sensor is about 1 piece away from touching the ground. Next, you want to look for these gaps in the shield and fill them up with with your own pieces. And now you have a color sensor shield. Talk about the touch sensor and the placement of it on your robot. The touch sensor can be used to bump against mission models and walls and figure out where you are by physically bumping against it. And now you might think you have to attach this on the side of your robot to actually trigger it, but if you notice, the touch sensor actually has a cross-shaped hole in the middle, meaning you can attach pieces and axles to it to route the button somewhere else or to create some sort of bumper. This way you can practically attach it anywhere on your robot and route it through axles to places you want to be triggered.
That's all for the video. Thanks for watching.
So to review on what they were talking about, they were saying that sensors need to be a good distance from the drive wheels for them to be able to line follow. And sometimes placing them too close to the wheel causes problems with the line follower. So you always want to make sure that your color sensors are good distance away from the wheels so that your robot can be the most efficient. And the gyro sensor can be placed anywhere, but must face a certain direction. It must face straight or it can face backwards, but you don't want to face side to side. And the other sensors need to be placed where they are most useful. So maybe on the side of the robot or on the bottom side. And when you're programming your color sensor, it can be affected by dirt, folds, bumps, or wears or marks on the field. So you always want to make sure that your field is as clean as the fields during the competition will be, so that your robot will run the most efficiently. Are there any questions?
Looks like we have no questions at the moment, so we're good to proceed.
We have a new core values tip. We will hear from our core values expert on what she has to say now.
You too. All people have different weaknesses and strengths, but if we all work together, we'll go amazing lengths.
So this is also in part of what she was talking about with teamwork. Everyone should be included. No one person should take all the work upon themselves. Everyone should be included and a part of the team and work on all aspects of the team. Now we're going to talk about motor placement. So if you are using the EV3, you can add 2 additional motors of either type, either a medium motor or a large motor. And you place them depending on where your attachments are. So if you're trying to stay based off the city shaper mission, if you were trying to lift the bat or so, you would put the attachment on the front so you could put an arm so you could lift the bat, or you could put it on the back if you're trying to attach it to a spinner or gear or something. You want to take these 3 questions into account. Do you have to do a task up high or low to the mat? That will determine if your attachment is high or down low. You want to be able to add attachments to the motor quickly and easily so that during your competition, you won't have to try to rush and get the attachments in. You'll easily be able to take it off and put it on because your mission is time. So that will take time away from you getting more points. And you also want to know if your robot is still balanced after adding the extra motors. You always want your robot to be balanced so that your performance is perfect. Now, here's a little chart that you could put in your files. So you want to know how many large motors, medium motors, color sensors, ultrasonic sensors, touch sensors, gyro sensors, I mean. You want to know how many you have, and the judges, they want to know how many you have. They want to know which ones you use. They want to know why you chose them. They also want to know which missions you use them on. So you could use the chart I was telling you about earlier, where you put all your missions throughout the season. You could put that on that chart also. And they want to know if you use them in a sufficient or novel way. They want to make sure that you took everything into account when you were planning your missions and adding your sensors and motors to your robot. Now we're going to watch a video about choosing the best wheels.
Choosing the type of wheel is an important part of an FLL team's design process, and there are many wheels to choose from. Here are 2 main things to think about when picking out wheels for your robot. The first thing to consider are the sizes of your wheels. Obviously, the larger your wheels are, the faster your robot moves around, and as a result, they will give you more time to target more missions. However, you should also remember that LEGO motors have a little bit of backlash or play, and that the wheel can move slightly without the actual motor moving. What's happening is that the gear connected to the motor shaft inside the motor can move because of the accumulated gaps in each gear, and the larger your wheels are, the greater this backlash will be. As a result, large wheels will be less consistent than smaller wheels. Now, the differences in this demonstration may seem small, but they will accumulate and you will see a greater inconsistency in a long run. The second thing you should think about are the thicknesses of your wheels. I recommend using thinner wheels because they will not make your robot unnecessarily bulky. In general, you should try to build a robot as compact as possible so it can maneuver tight spaces on the field. To summarize, if you want a robot that can get from point A to point B as quickly as possible, then motorcycle wheels are your best option. It will allow you to build small, compact robots, and the slick tread pattern will not cause your robot to shake or vibrate unlike other treads. However, you will have to use more advanced programming to compensate for its increased backlash. But the overall best wheel is a 62.4mm wheel. They are larger and therefore faster than the wheels provided in the education set, but they are also small and thin enough to allow you to build a compact robot with decreased backlash.
Okay, to review what we learned, we know that larger wheels may be faster, but are less precise and have more slack. So you always want to decide what wheels you're going to use based off of what missions you're going to do. Smaller wheels are slower, but they are more precise and more accurate. And back wheels, like the caster ball, need to be able to move in all directions and at the same height as the front wheels to be able to performance efficiently. Now we're going to talk about attachments. There are two types of attachments. First, there's passive, and then there's powered attachments. So an attachment is a mechanism you build that can assist your robot in completing a task. So dropping off or picking up an object on the field or in any aspect of robot design. This mechanism is attached to the base robot or to the motors. So that's when passive or powered attachment comes into play. And for a competition robot, the goal is to design attachments that work consistently. You always want your attachment to work every single time. You don't want there to be any mistakes because mistakes can happen at the competition and that won't be good for your team. Now we're going to watch a video about passive attachments.
FLL teams can have a maximum limit of 4 motors. Whether that's 4 large motors, 4 medium motors, or a mix of both, the grand total has to equal 4. There are two main ways teams deal with this limit. The first is to build attachments that can do multiple missions, but this usually requires a lot of coordination. The second is to build many attachments where some don't need a motor. These non-motorized attachments are called passive attachments, and they are great because the more missions teams can go for per run, the higher their potential points are. They are connected to the robot the same way as any attachment and they complete missions while only using the robot's general driving motion. With that being said, here are 3 types of passive attachments. The first are slopes. There's not really a formal name for these, but they are any angled pieces used to lift up or press down mission models. For example, in the recent crane mission, teams had to lift a lever to release a blue unit and press the right lever to rotate the crane. As the robot drives forward with a slope, the lever will slowly be forced upwards due to the angle of the Lego piece. And of course, if the lever had to be pressed down instead, the angle of the piece would just be inverted. The second type of passive attachments are dumpers. Dumpers are mechanisms that will release an object after it has come into contact with a wall or a mission. For example, in the City Shapers mission designed for wildlife, teams would receive 10 points for placing the bat onto the tree branch. One possible solution would be to create a dumper that would release the bat after it has come into contact with the tree. The last type are one-way doors, which consists of a box and a flap that can only open one way. One-way doors are a great replacement for mechanical arms and they are extremely effective at grabbing loops, which are very common in FLL, as well as pretty much any other object. The only thing you have to remember when building one-way doors is that the flap has to be proportional to the length of the box. If the flap is too long or the box too short, objects won't be able to enter.
Okay, now we learned that passive attachments do not require any external power, so they are used based off of the movement or gravity of the robot. Like he said with the treehouse one, when you move the robot straight, then the one-way door, then the flap will go up, and then it'll lock it in. It needs no motors for that. But the ones we're about to talk about, they do need motors. Those are called powered attachments.
FLL teams build their attachments directly onto their motors and then are forced to plug in their wires while switching out different attachments. This not only takes a lot of time, but it also limits how many attachments teams can build. In general, all your modular attachments will be connected to the robot through a universal mount. Your medium motor will then transfer power into your attachments, which have to be able to be easily removed. The first step to making modular attachments is to have your medium motors integrated into the robot with its motor shaft easily accessible. Next, you need to build some sort of attachment point where all your attachments connect to with connector pins that can't be pushed in or pulled out. And then you will build all your attachments off individual construction frames. So you'll have one frame for your universal mount and one for each attachment. Of course, you don't have to use construction frames, but they are extremely versatile due to all of their available studs. Finally, you need to choose a system in which the medium motor can transfer power into the modular attachment. Axles are the simplest solution because they can easily be inserted and removed from the motor shafts. However, due to the small size of the motor shaft, it can be difficult to insert the axle every time. Another solution are dog gears. Dog gears are a two-part clutch system in which the motor rotates two rounded pegs, which then rotate a rotary arm connected to the attachment's axle. Now, as you can see, you can use two rounded pegs with a 4-knot gear, or 3 rounded pegs with an axle bush, which was the original dog gear designed by Builder Dude 35. The advantage to dog gears are that they are easier to put on and that they interlock on top of each other, saving space. The last way to transfer power is to use gears. You simply need to attach a gear to a motor and another gear to the attachment. Gears are by far the fastest of the three solutions because of how small the teeth are. Also, if you do use gears, I highly recommend building some sort of frame holding the two gears together. You just leave one stud of room on each of the axles as well as an available stud for the opposite axle. This way it's physically impossible for the two gears to separate. If you don't do this, then there's a chance that the gears will skip if the attachment experiences any resistance. Overall, modular attachments will save your FLL team lots of time and base and will make all your attachments more efficient.
So as you learn, powered attachments need some type of power source like a motor or the brain to be able to function. And these includes motors, pneumatics, and other sources, like I said before. We will include a reference sheet that shows you how to build these attachments and how to construct them for your robot. Any questions before we move forward? Are there any questions?
Good. If there's no questions, I guess we can move on. And also, if you have a question when we're presenting one of the slides, please make sure you type it in the chat box.
So now we'll talk about navigation. So what is navigation? And this is what we'll learn.
Hello future scientists and engineers from us here at Milford Robotics. In this video, we're going to go over some general principles and helpful tips for reliably navigating your first LEGO League robot around the FLL robot game field. When you're programming your robot to navigate the FLL game field, there are only 3 things that you need to keep track of to know exactly where your robot is in the field. Those things are called degrees of freedom, as in the directions the robot is free to move in. In a 3-dimensional space, there are 6 degrees of freedom. 3 linear motions, which are forward, backward, left, right, and up and down, and 3 rotations called yaw, pitch, and roll. The nice thing about the FLL field is that we only have 3 degrees of freedom to keep track of. Those 3 degrees of freedom are the robot's north-south position, its east-west position, and its angle, which we'll call the robot's head. In other words, we need to know where the robot is and what direction it's pointing. If you're not familiar with the north-south, east-west terminology, take a good look at your FLL field map. The mat always has a compass printed on it. North is always towards the other team's table on the wall where the shared mission is located. When you're programming the robot, it is helpful to think about the position in terms of north-south, east-west, and heading. Here's a few strategies we'll talk about more in future videos. Make sure that you start in the same place every time. You can't know where you are unless you know where you've been. When you set up your robot for launch, you can line up on the marks on the field map, or, better yet, use a fixture. Either way, make sure you start in the same north-south, east-west position and heading every time before you launch. Bump into stuff on purpose. The table walls are your friends. Intentionally bumping into the field walls is a great way to reset your position and heading. Sometimes you can even use the mission models in the same way. Sensors are really essential for reliable navigation. A single color sensor will work to reset your north-south or east-west position by looking for printed marks on the map. If you use 2 color sensors, you can even use the lines on the board to reset your position and your heading. We'll post more how-to videos explaining the specifics of these navigation techniques in the future, so stay tuned. If you have any questions, feedback, or ideas for videos you want to see, leave us a comment. Till then, thanks for watching the Milford Robotics channel.
So thank you to Milford Robotics for explaining navigation. So as they said, navigation is getting your robot from your base to where it needs to be. And it also has to be reliable and repeatable. Just like the use of attachments, you don't want it to fail when you're in the middle of competition. You always want it to be able to do it multiple times consistently. And to accomplish this, you need to learn several strategies. First, good navigation will use some of all these techniques like aligning in the base. You can see that they used a jig in the base to align the robot along the squares. Wall following. A lot of people use wall following with wheels. We'll see that in the video on the next slide. Aligning on the lines. They can use the color sensors to line follow, and they can align on the walls to also help them reset their points, their position. Now we're going to watch a video explaining the jigs and all of the alignment.
Hi! In this video, I'll describe how my team uses jigs, a frame, and side wheels to align the robot during the FLL game. Here's my team's robot from the Into Orbit robot game. It has a frame around it that we use to align with the table and jigs before starting a mission. To make the alignment simple, we align the back of the robot against the wall and the side of the robot against the jig.
The jig makes the robot start in the right direction and so it is not rubbing against the wall. We pull the jig away before starting the robot. Different jigs allow the robot to start at different distances from the wall.
Our robot has side wheels, so it can roll along the wall and stay aligned with the wall. It's easy to program. We just have the robot turning a couple degrees into the wall while driving. The frame can also be used to align the robot against the wall. Just drive against the wall and let the wheels slip as the frame aligns the robot against the wall.
So that was real good information to teach you about the use of jigs and wall alignment. We will also share this video in our reference sheet so you guys can reference back to it. Now we will talk about cable management. So it's always important that your robot looks neat and is very organized, because if your cables aren't managed correctly, your missions can be very messy and it can affect the output of your competition very badly. So you always want your robot to look nice. That's a part of aesthetics. And for convenience, you want your wires should be in a way of where you could easily operate and remove them from the robot. You want to be able to identify where they go. So say port C and D is for motors. You want to be able to easily take them out and put them back in. So this is a little bit extra, but engineering notebooks, engineering journals, a lot of people use different words for it. It's very important that you use it. One, it's a way that you can let the judges know what your team is doing throughout First LEGO League. So outreach events, team meetings, brainstorming ideas. You can record your research, your field trips, and test your solutions. You can document your designs and how you built your robot. You can also put photographs and drawings in there and your plans for the next season or tasks that you want to complete or future ideas. Right now, we're going to show some of our teammates and they're going to perform their missions on the field from the 2019 City Shaper event. And they're going to talk about the robot and how they did it.
Hello, I am Miles MacArthur and this is my robot. It has a drivetrain, a gyro sensor, and some passive attachments. The robot's drivetrain has two symmetric powered wheels and an unpowered caster. It uses its gyro sensor to figure out when it reaches the top of the ramp. It has a rear attachment for pushing into the crane, a removable side attachment to release the swing, and a front attachment used for two pushing missions and for robot starting alignment. It can also do multiple missions in one run.
Hello, my name is Victoria, and this is my robot. It uses two color sensors and one touch sensor to make the programs run smoothly and accurately. The robot targets the Treehouse mission and the Build and Design mission. For each of these, it makes use of color sensors to find its location and align to the right position. To ensure that the robot is lined up properly before each run, I have built a sturdy jig and used a touch sensor to start the programs without jolting the robot.
So that is what our team did last year. So your second training will be October 16th. But for now, that was our presentation of robot design. Thank you for coming, and we hope to see you next time.